In high voltage applications, transmission lines HVDC, a single diode cannot meet the high voltage ratings. So power diodes are connected in series to increase the reverse blocking capabilities. So in forward bias, basically this way, diode 1 and diode 2 conduct the same current because they are in series. But when reversed, so when you have current flowing this way, in reverse bias, you basically have blocking voltages because the diodes withstand the flow of voltage. And due to manufacturing tolerances, the blocking voltage of each diode will be different. So each diode will carry the same leakage current. So when you're in reverse bias, you have some leakage current that still manages to flow through the diodes, and you also have blocking voltages. So the issue is we're going to have different values of voltage, of blocking voltage, and because of manufacturing tolerances, one of them may be too high for the diode to withstand, so you want to make sure they're split pretty much equally. How can we do this? The solution would be to force voltage sharing. So VD1 is going to be the same as VD2. And how do we do this? We connect a resistor across each diode. Connect the resistor across each diode so that the leakage current of each diode will be different. So you can kind of manipulate what your value is going to be. So let's solve an exercise. Say we want to find the diode voltages V01, V02. You want to find the diode voltages if you know that the voltage sharing resistances R1 and R2 are equal and have a value of 100 kilo ohms. You also know that the reverse leakage currents of the two diodes, IS1 and IS2, are 30 milliamps and 35 milliamps. And finally, that the two diodes are connected in series in order to share the total DC reverse voltage, so VD, of 5 kilo ohms. So where do we start? We're going to write down what we know in terms of voltage and in terms of current. So in terms of voltage, what we know is that the voltage across diode 1 plus the voltage across diode 2 is going to be equal to the DC reverse voltage of VD, which is 5 kilovolts. In terms of current, what we know is that IS1, so the reverse leakage current across S1, across diode 1, plus the current across resistor 1 has to be equal to the current through reverse leakage current through diode 2 plus the current flowing through resistor 2. So we started here. IS1 plus the current through resistor 1, which is going to be the voltage across D1 over the resistance across 1. And we said this equals the leakage current in diode 2 plus the current across the resistor 2. So VD2 over R2. So this is what we know. Let's rearrange our first equation so we can plug it in. Let's say VD2 is VD minus VD1. This we can plug in here for VD2. So we're going to have IS1 plus VD1 over R1 equals IS2 plus VD over R2 minus VD1 over R2. This is this, because we substituted this. Now, look at our resistances. We can simplify this because we don't need the subscripts R1 and R2, because our values for R1 and R2 are equal, 100 kilo ohms. So we can simplify further. We can do VD VD1 over R, then bring over the values divided by resistance that you have from the other side and equate it to the values of current, IS2 minus IS1. Now simplify further, so we have 2VD1 IS2 IS1 now we can times by R and divide by 2. So 2VD1, it's going to be R, 2 minus IS1. Now we're going to divide by 2. Now we're going to take this to the other side. So you have plus VD plus whatever this is. And what's left, we just need to plug in our values. So the voltage across the source was 5 kilovolts. The resistance across the resistors was 100 kilo ohms. And IS2 minus IS1, IS2 minus IS1, 35 minus 35 milliamps minus 30 milliamps. So your final value for voltage sharing across diode 1 is 2750 volts. Now we can find the voltage across diode 2 to be VD minus VD1. So 5000 volts minus 2750 volts. So the value of voltage sharing across your second diode is 2250 volts. That's it.